aerosol. So let's address the statement of the problem. When a water jet floats for a small aperture, an aerosol may be formed. Investigate the parameters that determine whether an aerosol is formed rather than jet. For example, what are the properties of the aerosol? So we understand that first we need to make an experimental setup that allows us to read the parameters. Then we need to study the breakup mechanism of the jet into droplets and find down the role of air. Also, we need to find the aerosol properties and then analyze our work. So, firstly, to solve the problem, we need to define some basic concepts. It is that aerosol is a dispersed system which consists of small particles suspended in a gaseous medium. Size of the particles in the aerosol vary from a few millimeters to the power of -7. So, therefore, in the literature we can find two methods of obtaining aerosol. First, it is a dispersed aerosol and concentrated aerosol. The statement of the problem determines the method. Therefore, we will see that it will be the simple mechanical structure, and some issues related to the ultrasound or the electrical effects are not observed at all. So, after that, you'll see that there are two mechanisms of jet disintegration. First, it is instabilities and perturbations which arise in the jet itself. The reasons of them is the cavitation and turbulence flow. So the cavitation is essential when we talk about ultrasound. Therefore, we will consider only the transition from the laminar to turbulent flow. And the second one is the jet disintegration due to the interaction with the air. So after that, we understand how to make our experimental stuff. It consists of the pump flowers in the container of water, the tube, the rod, and then a nozzle with a round apertures. So, what about fixing our experiment? So, we will use the camera. The diaphragm goes open as much as possible. Therefore, the depth of field will reduce as much as possible. So, we will consider focus on the Y, and therefore, we will consider the small plane of the picture, and after that we'll find out approximately 50 droplets and see the size of the droplets, we will consider only Z droplets which were sharp in the picture. So after that, we understand that we need to find the criteria which shows us the difference between laminar and turbulent flows. So the Reynolds number is a criteria for the hydrodynamic similarity of the viscous fluid flow, including the ratio of internal forces to viscous friction forces. It is so therefore we'll consider that if the number of Reynolds will be smaller than this number, we will consider completely laminar flow. The mechanism of breakup will be the laminar plateau. The Rayleigh plateau, and the size of the droplets will be bigger than the jet. If we consider the number of Reynolds in this range, we will consider that the length of the broken part begins smaller and the size of the droplets begins smaller, but the number of droplets increases. So if we talk about the number of Reynolds which will be bigger than that, we will consider that the droplets will appear immediately near the orifice, and the jet motion is completely turbulent. So after that, let's consider the completely laminar turbulent flow. We will consider the Rayleigh plateau instability. Therefore, we will see that the time of the jet break up into the droplets don't depend on anything, and the diameter of the particles will don't depend on the velocity and the speed, and the time of the broken of the jet don't depend on the speed. Therefore, we will consider that. So why we can find out the Rayleigh plateau instability. So let's assume now that we have a small perturbations of the jet. Therefore, we will have a different radiuses of curvature, and we will have different forces which are acting in our system. So we understand that we have a different pressure under the curved surface, and therefore the instability will arise. So after that, we can find the dependence of length of the broken part of the jet on the velocity. So we will see that we determine that the length of the broken part of the jet will be like this. So we can plot these dependencies, and we understand that we can approximate it linearly. So we found out the time of the breakup into the droplets don't depend on the velocity. So after that, if we will increase the Reynolds number, we will see that semi-turbulent flow and the turbulent flow, the size of the particle decreases, but the number of particles increases. Therefore, we will consider. So we will see that the length of the broken part of the jet will be like this. So we will measure it like the if with increasing the Reynolds number, we will see only the turbulent flow. After that, we'll understand that, for example, let's consider the path of the jet. It goes to the aperture. Therefore, the flows meet each other, and we will have something like this. So, with increasing the velocity, we will see that the angle of the expansion increases, and well, let's understand why. So, if we consider again the part of the jet, so we will see that we have we have a velocity profile of the jet, and near the aperture, we will see that the velocity of the jet will be 0, and the velocity in the jet will be not 0. Therefore, we will see that it will be we will see that after that we will have a motion. The drop will rotate because of the difference of the speed. So after that we will combine that three graphs for the length of the broken part of the jet on the velocity. Therefore, we will consider that we will have this, and with the increase in the velocity, the size of the particle decreases and the number of particles increases. So from this graph, we will understand that why we can see that the particles are too small. So in literature, they say that we have a big role of air, but let's make an assumptions and find out is it real or not. So first of all, it is the airflow is capable of deforming the jet, thereby increasing the disturbances that has arisen. So we did an estimation for the diameter 2.5 millimeter and 1 millimeter, and we have velocity 10 or 16 millimeters per second. We walked at significantly lower speeds, therefore we understand that it's not our effort, and this is not the reason why we have so small droplets. So after that, the second effect is the entrainment of the water flow by the airflow is significant. So we have an estimation, and we have this speed. Sorry for that. We have We have this speed. It is too big, and we understand that it's not our effort at all. So the role of in our situation is not a fact in the observed effect. So why? Okay, let's consider situations that we have raindrops which fall down and they don't divide into the small droplets. So why? We understand that it is really important that we have internal perturbations in the jet itself. So and these perturbations are characteristic. The characteristic of this perturbation is the number of Weber. It is the criteria which shows us the ratio between the surface tension forces and dynamic pressure force of the liquid jet. So it depends on the velocity of the jet, the diameter of the jet, the density of the jet, and the coefficient of the surface tension force. Therefore, in the literature, we can find that if the number of Weber, with increase in the number of Weber, the size of the droplets decreases and the number of droplets increases. So we understand that after this Reynolds Weber, we will consider that we have a different size of the droplets. Therefore, we will make this dependence, the probability on the size of the droplets. Therefore, we will consider that we will have an average diameter. It is for this situation, you can see this on the slide, and the function of this distribution will be normal. So after that, we understand that we need to find out the size of the droplets, and we will consider the function of Weber, and we will make an assumption and that it is linear. So if we know the number of Weber from the initial properties of the jet, we will have the average diameter of the jet. So after that, we studied the optical properties of the aerosol. When light passes through an aerosol, its scattering and absorption are observed, and we will not confuse light scattering on the water droplets with its absorption by the water vapor molecules when the light passes through the droplets. We checked the feasibility of this law for aerosols experimentally. The distance between the light source and the photosensor was fixed, but they placed them in the different places on the aerosol, closer to the aperture and in the bigger distance. So we changed the concentration and could establish the dependence of concentration of the aerosol particle. These dependence are shown in the slide. In the aerosol particles are quite big, therefore we will consider the mere scattering, and it will be absorbed. jet the wavelength of the light. Therefore, we can say that in the dependence we see that, and we understand that it is a mere scattering. So the next one is the electrical property of the aerosol. We understand that we have a friction between the jet and the aperture. Therefore, we will consider the redistribution of the charge in the jet itself. Therefore, we will have the different particles. Some of them will be positive. Some of the particles will be positive. Some of them will be negative, and some of them will be neutral. But all aerosol will be electrical neutral. So we did a lot of work, and for example, we found out the method of obtaining aerosol by simple mechanical spraying destruction through a small aperture. The mechanism of jet integration into droplets and the dependence of droplet size on the liquid velocity was studied. So we find a way how to find out the sizes of the aerosol from the initial parameters. So as also the qualitative level, while we can see the different modes of the aerosol, we found out the influence of air and understood and estimates its role in our effect. And also we find the technical for estimating the size of the droplets and studied optical and electrical properties of the aerosol. So thank you for your attention.
Thank you very much. Now we have time for opponent to ask their questions.
Have you checked some else orifices than simple orifices, like jet nozzles?
Yeah, we changed it, and we changed the what
But
question?
as I understand, only the radius of nozzle.
Yeah, only the radius of nozzle.
Okay, thank you. If the flow is fully laminar, would the atomization still occur?
Yeah.
Okay. Did you obtain a laminar flow in your experiment?
We yes, we obtained it, and it is really the simple situation how we can make it.
Okay. What is the maximum angle of spray?
For our situation, I have 104 degrees. So I will write this one. I can do it.
Okay. Right. Was your pressure in the atomizer constant?
Yeah, it was because it was a pump. We have a pump. It's like.
How did you check it?
When we check it experimentally, we can see that so we can find out the way it's experimentally how to check it.
Right. How exact was were your measurements of droplet size?
You can see it in the picture, but so we have a lot of ones and
You mean 50 particles?
50 particles from each photograph, which were shared.
Okay. Right. Are you sure
Okay,
that?
sorry, yeah, your time is up. Thank you very much. Now there is time for the presentation.
Right, my name is Michał Janik from Team Poland. Today I have a great pleasure to present to you our opposition on problem number 2, which is aerosol. First, let's look at the problem content. It states that in our understanding that that small aperture means that we have to investigate the sufficient numbers of nozzle atomizers varying in their geometry and shape, which wasn't fulfilled at all by the reporters. They didn't also investigate and determine the properties of aerosol according to some K parameters. Some theory models, for example, for temperature dependence, were lacking. Also, they didn't. However, there were some additional values. They didn't measure all the properties of aerosol correctly, which is droplet size distribution in the flow and angular distribution. So that was fulfilled only partially. But let's move to the pros of the presentation. The definition of aerosol was clear. We also like that the Reynolds number, which is some key thing in this problem, was good. And additional thing was electrical properties. That was very nice. Right. But moving to the cons, they didn't obtain the sufficient measurement adequacy. We mean by that they examined only the middle part of the jet, and the droplets which were measured were only the sharpest ones, while because the other ones that were not sharp were probably moving with higher speed, and of course they were with some other sizes. So we think that that was not well examined. But the main con of the presentation is, in our opinion, only the simplest option for an atomizer examined, which is plain pipe. While there are plenty other types of atomizers, including simple cone atomizers, but also more complex geometries like pressure swirl or other. There was no theoretical predictions of most of aerosol properties, like, for example, mass distribution. And other key is that they neglected secondary atomization, which is the impact of aerodynamic forces. Because if the flow is laminar, there is no turbulence, but though atomization can occur due to air. Thank you. Let's moving on to discussion, I guess. Right. So why is that he didn't investigate maybe some more orifices?
You think about the apertures. Okay, I explained it. Firstly, we consider the small aperture as a shape of a circle, but we understand that if we will increase, for example, we'll be something like this, or something like this, that the aerosol will change. First, if we'll talk about this one, the disturbances which arise in the jet will be really big. Therefore, we'll see the aerosol
But
in
as far as we heard, you didn't mention it in your presentation, I guess. But if you will, I mean that not only the cross section of the orifice, but also the inner build of atomizers and most matters.
You mean something like this?
Yes, I mean it's something like this, for example, but it's also a single case. I mean here, very often appears like some objects inside of atomizer in order to obtain fine droplets.
Because in our situation, we can control our setup. We can find a way how to investigate it, and we understand that if we will have something like this or something like this, we will find a way how to measure it and how to understand what is happening.
Yes,
So
exactly.
in your situation, we can't do this.
Yes, exactly. So in our opinion, although some cases were investigated, this is the field of improvement. But I also would like to ask you, how did you exactly obtain velocity of the jet?
Андрей. So we have a different profile velocity. First, for the laminar flow, it will be something like this. So if you consider the laminar
Right,
flow,
but I mean the.
I understand, and I explain you now. So, дальше, пожалуйста, вернись обратно. Laminar jet. So we will have a different pressures inside впереди на laminar jet. And if we will consider this one, we will have a different pressures inside, and therefore we will consider the largest velocity. And if we will talk about the turbulent flow, пожалуйста. We'll talk about like this, and we will have a mass flow rate. Therefore, if you will consider the turbulent flow, it will be something like this, the profile velocity, and therefore we can find, therefore we can measure our velocity by this formula. It is the mass flow rate, and it helps us to find the average value of the system.
I get it. The method of measurements of droplet size also struck us. Are you concerned that they are very accurate?
We find out that, for example, in this.
Or did you maybe provided some theoretical model to determine the droplet size, for example?
We found the errors for this question, and it was too small, therefore we can see that it will be equal in our situation.
Right, but let's go back. So what was the accuracy of your measurements?
I said that the accuracy is bigger if the errors are smaller, so we can see that the errors are too small, therefore we have a big accuracy.
Right.
Accuracy.
Are you as far as we are concerned, there exist some other methods of measurement droplet size, which because this is some area of improvement in our opinion. So, for example, some chemical using some chemical substances in order to get a plate with droplets on it, so that we can watch the plate.
You mean the different
With
viscosity?
microscope. No,
For example?
I mean some other measurements methods.
I understand.
There are some methods that have bigger accuracy as far as we are concerned. Have you measured the?
We have a lot of ways. For example, the first way is the way
Right,
that we use.
But we are interested in what you exactly did, not what are the methods, because we also.
Exactly. I said that I see that if, for example, I have a photograph. Sorry.
Like you mean the average diameters? Right.
Yeah. So we have a photograph
we
and
think
break the
that-
sharp ones, and therefore we'll consider these ones which were sharp, and then we have an average diameter
Yes,
from the photograph.
we are well aware of that. And which diameter have you used?
We use the average diameter of the droplets.
but which one? There are various types of,
Slides video.
including the
And that
distribution
was
of masses of.
so we for example can see this. So we will then we will
Oh,
have
southern diameter. Okay.
yeah.
Now we can proceed. Have you investigated the velocity profile of aerosol of different particles of aerosol?
So you think the method is correct?
Yes, this
Okay.
is the correct method, but although this is the correct method, of course, the diameter, we think that the measurements was highly inaccurate, according to
Okay.
examining only a part of volume and some little particles. Were the particles in your aerosol circular?
Then circular, we understand that we have perturbations inside. For example, if you consider the small droplets, we have the turbulent flow in it, therefore it will look like this. For example, or something like this, because it's not a regular flow and we can't have this one.
So how you determine the diameter of this droplet?
We see in the picture that we have something like this, and we find the average. We can find how many pixels were in the picture. Therefore, we can obtain that. We can say that the volume of the. We can find the average volume for the particles. So and. Are you agree with this method or not? Or you have another way how we can measure it or something like this?
This is a good method, I think.
So-
But approximation, of course. So
Okay, you have some errors in this situation, but we
Right.
can control it.
right, what was the angular distributions of droplet? Because in your methods you didn't exactly include a method for measuring the size of droplets in different sectors of spray as you measure on the.
You mean that if, for example, we have the jet, we have the aperture here, yeah? And then after the aperture we will have spray like this. There will be the biggest one and there will be the smallest one. You mean this slide or what?
For example, yes.
So we have a different distribution, of course, because in the center will be the biggest one. So in the center we can see that we will have the biggest droplets, and in these places we will have the smallest ones because we will have dividing the droplets.
Have you checked though the sizes of those small ones? Because this is also our interest.
It's not interesting for our situation because it's not like a property of the aerosol in my opinion. So I can explain why we can see the difference this way and
I would be more interested in how did you exactly check the constant pressure of your pump?
the pump is
We consider
in
the
the pump
pressure
we
level.
have. Okay, I understand you. In the pump we have a device with which controls the pressure. So our pump knows we know the pressure of the pump, and therefore we can make our experiment.
Well,
So it was
right, but
controlled by the pump.
in our opinion, the pressure is not constant. And also, there is no time, but we have to mention the temperature which was measured, and it differs viscosity.
Sorry, but our pump can work on the significant
You will have temperature
Oh,
at
right.
the end. Thank you very much, because now we have time for opponent to summarize.
Right. To summarize the discussion, I would like to say that although fine qualitative explanation for simple orifice was found, there was no investigation of more complex geometry of nozzle. Also, the measurement methods had some big flaws that were, in our opinion, that could be